Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 14, Part 2, Factorial Treatment Structure. So in this section, we're going to be talking about testing the significance of interaction terms as well as the main effects. So if you have a factorial treatment structure, that means that you have two different factors where you're going to randomize people into the many combinations of those factors. So let's suppose that on factor A, we have A levels, 1, 2, all the way down to A levels. And on factor B, we have B levels, 1, 2, all the way down to B. If you think about it, at the end of the day, you're going to have A/B treatments total, okay? And what you might ask first is there an interaction between factor A and factor B? And so what you're going to do is you're going to first test if the interaction is equal to 0 versus are at least one of the interaction terms different than 0. Okay, we can do this by using an ANOVA table and calculating our sum of squares. That should have a bigger parenthesis around it. Our sum of squares for the interaction term AB divided by the degrees of freedom for the interaction term, and then our sum of squares error divided by our degrees of freedom for the error term. So overall, you're going to take the mean square for the interaction term and divide by the mean square error. Now, if the mean square of the interaction term is no different than the mean squared of error, then you're going to end up having an F distribution where it peaks at 1 and ends up being skewed right. So what's going to happen is you can set up your rejection region, reject HO. Let's set alpha equal to 0.05. Remember, there is nothing special about 0.05. We're just trying to have some sort of level of our type 1 error rate. So alpha could be 0.0001. It doesn't matter what you set your alpha level to. It really depends on the context of the problem that you're dealing with. But you should set this before you actually do your study, and you're gonna set up where you fail to reject HO. So once you've calculated your test statistic, you can see, is your test statistic right? Here's your critical value, F critical. And then you're going to calculate your test statistic, and either your test statistic will fall to the left of your critical value, and this whole area here, that will be your p-value. And if your p-value is large, then that means that you don't have much evidence against the null hypothesis. You don't have right? If you see something unusual where your test statistic is beyond your critical value, then this area will be your p-value. And your p-value will be very small, and this is increasing evidence against HO. All right, so in general, if you want to make a decision, if you observe a very large test statistic, that means that the interaction term has a lot more error than just random noise. Your mean square of your interaction term compared to your mean squared error is very large. And that means that there's something more than just random error happening. And so when our test statistic's very large, our p-value is going to be very small, and we're going to reject HO. And when we reject HO, we are thinking, hey, we really should have this interaction term in the model. Okay, if our test statistic is very small, that means that the mean square of AB is not significantly bigger than our mean squared error. So it's no different than noise. And for a small test statistic, we have a large p-value. When we have a large p-value, you don't have enough evidence against the null to say that it's possibly wrong. And so you're going to say there's not a significant interaction between factor A and factor B. So once you complete this, if your interaction term is significant, you should stop. And you say, we're going to keep the interaction term in the model. And in that case, I'm going to keep the main effects as well. However, if the interaction term is not significant, you might be asking yourself, well, does factor A matter or does factor B matter? So you could repeat an F test to test if there's a significant effect for factor A. Okay. And remember, you only do this if the interaction term is not significant. Because if it is significant, you're going to leave in the term for the main effect anyway. So there's no reason to carry out this test. All right, how do we do this? Well, we ask ourselves, are all the effects of factor A equal to 0, the tau 1 to tau A? Or the alternative, not all the tau i's are equal to 0. We're going to calculate our test statistic using the mean square for factor A, dividing that by the mean squared error. You're going to compare this to an F distribution. And once again, the F distribution is skewed to the right, peaks at 1. You can set up your rejection region. You can set up your fail to reject region. You can get your critical value. Remember the area of the rejection region, that's equal to alpha. And from there, you can calculate your test statistic. And if your test statistic is not as large as your critical value, right? If your test statistic is not as large, then you're going to have a very large p-value, right? And if your test statistic is very, very large, then you're going to have a very small p-value. But essentially, this p-value is just giving you increasing evidence against the null hypothesis. It's not a magic bullet. You really do need to think about your study design. But overall, this can help you make a decision to know if that main effect, if there's a difference in the effects of the different levels of factor A, right? We can do the same thing for testing the significance of the main effect for factor B, but remember that we only do this if the interaction term is not significant. Now we're focusing on the betas because the betas have to do with factor B, and we're going to ask, are all the effects of factor B equal to 0, or are at least one of the different levels of factor B making a difference in our response? And we can calculate our test statistic by looking at the mean square for factor B divided by our mean squared error. Once again, this is an F distribution, and that peaks at 1. We can set up our rejection region. We can set up our fail to reject region. That's our critical value. So that value is the value in which we would determine that we have evidence that supports that we would reject our null hypothesis, and we'd say at least one of the beta J's are not equal to 0. I saw a double negative. HA, not all of the beta J's are 0. Or similarly, another way to say it would be at least one of the beta j's does not equal 0. Okay, so when we interpret this, we would say, if we reject HO, we're really saying there is a difference in the means for the different levels of factor B. Whereas if we fail to reject HO, we're really saying there's not a significant difference in the means for the different levels of factor B. So overall, we are doing an F test, right? But the way we're doing this is first by testing the interaction. If the interaction term is significant, you stop. If the interaction term is not significant, well, then we probably don't want that in the model. And then we just say, is there an effect of factor B? Is there an effect of factor A? Right? All right, I hope you learned something today, and I'll see you in the next video.